Hello, welcome again to the Data Modeling and Management course. In this topic, we will discuss about transaction processing and consistency model. First, have you heard of the term transaction? What do you think about when we heard of the term transaction? What does it mean by transaction? Let's spend a few seconds think about the answer to these questions. Alright, here would be my answer to the question of what does it mean by transaction. Within the database technology, a transaction refers to a sequence of actions that read from and or write to a database. And that sequence of actions, it can be a combination of any CRUD operations performing to the database. That means it can be an insert of a new data, it can be a read operation, it can be an update, or it can be a delete. And usually, we make a transaction to our database to correspond to a business transaction or to a transaction of the real-world operation that we would like to perform on our system. Think about, for example, a banking example. When you go to a bank, what would be a possible operation and transaction you would do at a bank? Of course, we can think of withdrawal, deposit money, transfer money, right? And when we are talking about, for example, withdraw money, what kind of operations we would perform to do a business transaction of withdraw money? Of course, definitely you need to read, right, how much money that the user have with his or her account. And after that, you need to also update the balance that the user withdraw from his account, right? That means an update to the account balance of that user need to be performed. So in this case, you can see that at least two operations are involved to complete one single transaction of withdrawal of money. That is, first, reading the balance a user has for his account, and second, update the balance to reflect the new balance of the account he has after making the withdrawal. You can think of other similar transactions at the bank as well. For example, transfer of money. It could be a little bit more complicated, right? It could be the case that one user wants to transfer money from his account A to another user, which is account B. So that means we need to also perform a few read operations. We read the initial balance of user account A and initial balance of user account B. Then the amount of transfer should be deducted from the account A and should be deposited to the account B, right? And that means corresponding updates to the account A and B for the new balance would need to be performed as well. So in this case, you can see that one execution and complete execution of a transaction would involve several database operations. And that is why transaction is important when we consider performing database operation. And when we discuss about transaction processing within the relational model and relational database technology, you might have heard of the term ACID. ACID, A-C-I-D. ACID is kind of transaction model that has been used and enforced a lot in relational database system. So, what is it? Have you heard of it? Do you know what ACID would stand for? Right. In ACID transactions in database, A stands for Atomicity, C for consistency, I for isolation, and D for durability. And what does it mean for each of these? Okay, so let's look at each of these acid properties in detail. First, atomicity. A transaction is considered to be an atomic unit of processing, which means that the transaction is either performed in its entirety or not performed at all, which means that suppose we have a transaction T, okay, transaction T, and this transaction T is the bank transfer, money transfer in a bank transaction example that we discussed previously. Okay, so this transaction T may consist of a few sequential operations, right? That is, suppose it is a transfer of account A to account B for a certain amount. So we definitely need to read account A balance, and then we read account B balance. Then we update account A by, of course, reducing the amount of the transfer, right? And then we update the account B by increasing the amount of the transfer. So atomicity ensures that when a transaction T is performed, the whole transaction, that means these four operations, must execute successfully in its entirety. That is, first read A, then read B, then update A, then update B. So entirety, that means the entire execution of all this, or not at all, meaning that we do not allow partial execution of the transaction T to happen. But how can we ensure that? Of course, it can happen that once the database executes transaction T, it may execute the first operation, second operation successfully, then third operation successfully, then the system crashes, meaning that it cannot continue the execution, right? But this will leave the system in an inconsistent state. Definitely, data will be wrong, right? Because we deduct the money from account A, but we have not updated or increased or deposit the money to account B. So once the system is up and running, the system will need to ensure that this transaction T that has partially executed will need to roll back to the previous stage before transaction T executes. That means the update to account A should be rolled back, meaning that money of account A, the balance of account A should be restored to the previous value, right? Then transaction T can consider re-execute later on. Okay, but we do not allow partial execution of the transaction T in the database. So this is to ensure atomicity. And this is the meaning of atomicity in database. The second is consistency. The term consistency here means that execution of the transaction, whether single transaction or concurrent transaction execution, it must move the database from one consistent state to another. And actually, if we can guarantee that every transaction is entirety executing or not at all, and also there are proper concurrency control of multiple transactions, then consistency can be achieved. Then the third property, isolation, meaning that A transaction should not make its update visible to other transactions until it is committed. Now we have another term discussed here, that is committed. We first talk about the term rollback, right? When we discuss about example of Atomicity of a transaction T, when we refer to bank transfer example. Commit means a transaction is considered to commit, mean that its entirety execution has been successful. So when a transaction T can successfully execute all operations within it, then the transaction will commit, and any changes, anything that has been made by a committed transaction will be permanent. Okay, so this is the meaning of commit. We cannot roll back a committed transaction. But of course, partial execution means that the system will roll back, right? Partial execution of a transaction, that means uncommitted transaction will be rolled back, but committed transaction will not roll back. So back to the isolation. Why this is important? It means that a transaction can be rolled back at any time because a failure could occur, right? So if the transaction can be rolled back, if a transaction that is not committed can be rolled back, it means that any changes made by that transaction will not be permanent yet. So other transactions should not see the update of the uncommitted transaction at all. For example, I may be executing this transaction T. Remember this transaction T that we are now discussing for the transferring of money. Suppose that we are executing this one. We read value of the balance of account A, we read the account B, okay. Now we update account A by deducting the amount of the transfer, right? But if other transaction, let's say transaction S, okay, we have another transaction S. Okay, let me write it here. Let's say I have another transaction S. That I want to deposit more money to account A. Okay. If at that time, of course, to deposit money to account A, what do I have to do? Definitely, I have to read account A, right? And then I need to update account A with a new balance, right? Okay, so what could be wrong here? Suppose that while the time I am executing transaction S, it needs to read account A. But if we read account A balance at the time that it has this transaction T running, it may happen that we don't know yet whether a transaction T will finally commit or not, right? So transaction S should not read that value of A at that time. Okay, so this is the meaning of isolation. A transaction should not make the update visible to other transaction if it has not yet committed, because it may roll back or it may commit, we don't know. So in the concurrency control of transaction, usually they will try to have certain mechanism that maybe it needs to have a lock to lock the data, not allows other transaction to read, or to wait until the transactions commit. But if we want to really allow concurrency control, there will be a lot of mechanism. But later on, transaction S cannot commit before transaction T if transaction S executes after transaction T, something like that. Okay, we need to wait until we know whether transaction T will commit or will roll back, something like that. Okay, so that is isolation. We need to make sure of this. Then the last one is durability. That means once the transaction is complete, meaning that it commits, it will make a permanent change to the database and cannot be undone. So this is already what we already discussed, meaning that committed transaction cannot be rolled back. Okay, here's the case. All right, so these are the 4 acid properties of transaction. Such acid properties of transaction is actually focused and emphasized by relational database. But now we also discuss about NoSQL database, right? So there is a big change. The change from centralized relational database to a cluster-oriented NoSQL database. And that big change really make a lot of changes on the concept of consistency. We will have a look in more detail. The important change in terms of the concept related to consistency in relational database to NoSQL will relate to the concept that we call strong consistency. That means actually in relational database technology, the focus is on what we call strong consistency, while in NoSQL, we usually give certain relaxation and consider various form and various degrees of consistency, not only very strong one. But of course, whether we would like to emphasize strong consistency model or not, it really depends on the application requirements. When we talk about the term consistency, there are actually several forms of consistency to discuss. The important one first is update consistency. That means think about 2 transactions trying to update the same piece of data at the same time. Do you think it will be a conflict? Yes, definitely. In that case, we call it write conflict. 2 transactions try to make change to the same data at the same time. So this is definitely a conflict, and the database technology should ensure that such a conflict will not occur, because it could result in a problem of, for example, we call it loss update problem. Okay, I will not talk into much detail, but think about 2 transactions again in the banking scenario. You have your account A, your bank account A. 2 persons, 2 friends would like to transfer the money to you. Okay, so if they want to write the data at the same time and both transactions, both transfer money transactions are successful at the same time. Initially, suppose, let's say you have 1,000. Okay, let me write it down here. Let's say account A, initial balance, you have 1,000 baht. Your friend X would like to transfer you 100 baht. Your friend Y would like to transfer you 200 baht. But if they do the execution of the transfer at the same time, so X would like to transfer 100, right? Y would like to transfer 200. Executing this at the same time, meaning that X will change your balance into 1,100 baht, while Y will change it to 1,200 baht. Exactly at the same time. Finally, whatever final update would be, then you have only 1,200 or only 1,100 instead of having 1,300, because that is supposed to be the last correct update that you should get, right? So this is one example of update consistency problem. Okay, so let's consider another case, which is called read consistency. Of course, read consistency will happen only when two transactions trying to perform on the same data, but one transaction is reading, another is writing. So that means you can read a value which is not yet finally updated. Okay, so that is why it is called read-write conflict, and it leads to what is called inconsistent read, and it leads to another problem which is called dirty read as well. Okay, there are quite a number of problems that could occur because we want to allow several transactions to concurrently executing, because you want to actually improve the performance of transaction processing, right? You don't allow everyone to wait until one transaction finish and the other wait, right? You want to have ability to concurrently executing multiple transactions at the same time. But with that, it means that certain form of consistency could occur. Certain form of consistency problem could occur. In the previous slide, we talked about update consistency and read consistency, right? And those two consistency issues could take place either in centralized database or distributed database. But now we are moving to another example, another form of consistency, which is called replication consistency. And in this case, it will occur and it will be the case when we are in distributed system of database. So with replication consistency, it means that you actually have several nodes of data across the network, across the distributed network, right? It is kind of distributed database system. So we need to ensure that these multiple nodes that contain the same data would be consistent, meaning that whether you read the data from any node within the system, you should get the same value from reading it from another node. So that is called replication consistency. Let's look at this example. Okay, now you see that suppose we have three nodes. Okay, here is a data node in Mumbai, and another one is a node in London and a node in Boston. Suppose that in Mumbai node, at Mumbai, Pramod, okay, this is, let's say that we are talking about hotel reservation system. So in this case, Pramod is the one who has booked the last hotel room on Mumbai node. But of course, since we are in the distributed system, right, the update that takes place on Mumbai node needs to be propagated, replicated to the other two nodes in London and Boston. Of course, the time taken for the synchronization, replication, or whatever could take some time, right? And if another user, Martin, in London, okay, he checks the room. If the update to London node has not been taken place yet, okay, that means Martin would see that the room is still available. He will not see that Pramod has already booked the room. So the update to London node has not yet been completed. And while if we consider in Boston node, Cindy has already seen that update of the last room, okay? So Cindy cannot make a booking, of course, while Martin maybe can make a duplicate booking. And this is an example of what we call inconsistent reads because of the replication consistency cannot maintain in good time. So this is an example of possible problem that could occur due to replication consistency if it is not controlled properly. Here we can discuss about two other forms of consistency. First, eventual consistency. This is a kind of relaxed form. Actually, remember, we say that when we have possible replication consistency here, nodes could have replication inconsistencies. Okay, but the concept of eventual consistency say that if actually there are no further updates taken place, right? Nobody is updating the database after the last update. Then eventually, all nodes will be updated to the same value. It is just a matter of time. That is what is called eventual consistency. Another term here on the same slide, you can see the term which is called inconsistency window. So this term is related to eventual consistency because it refers to the length of time that an inconsistency would be present. That means how long time will it take for different nodes to have the same data? Okay, so the time it takes for different nodes in the distributed system to have consistent data, that is called inconsistency window, the window of the time that data still remain inconsistent until finally the whole system becomes eventually consistent. Have you ever experienced this problem in this example? I think every one of us here is a user of Facebook and social media, right? Has it happened to you sometimes that you may post a message on Facebook or social media, right? And once when you refresh your browser or your social media application, that refresh goes to a different node to fetch the new post, the new updates, and so on. But that different node that the refresh takes the data from has not received your post yet because it does not make the replication consistency yet, and it has this inconsistency window, right? So after the refresh, you might see that your post has not been there on the system yet, but actually it's there, but it's there on different node, but you refresh data from other different node. So you may think that your post was lost, which actually not lost, but it goes to other node and it will take a few more time. The in consistency window time to make every node having all consistent data. Okay, and that could happen in sometimes that you may repost the same message again because you think that the message, the post was lost, so you repost that the same. And finally, you might find out later on, right, that you post a few of the same message twice or more than 2 times. With the previous form of consistency that we discussed, right? So here are some related forms of consistency. That is, first, user perceived consistency. So it is very important to have the user at least see their own data that they have made, their own updates that they have made. So user perceived consistency is or refers to the time expected by the customer or the user to see their own updated value. So we expect this time to be very small, right? Very short time. And then another form of consistency which is similar, that is called read your write consistency. So it's exactly to solve that problem that we previously discussed. When you post a message, you would expect to see that post immediately, right? Because you want to make sure that your post has already been successful. So with this read your write consistency, it means that the system should guarantee that once a user has made an update, the user is guaranteed to continue seeing his or her own update, even all the nodes has not yet been synchronized with the same consistent data yet. But at least the node that the user access the data from should always contain the consistent data related to the user update. And the last consistency form is called session consistency. Actually, this is related to the concept of the session in a browser or in a computer application. Okay, so it means that within a user session, there must be read your write consistency. So if you're still in the session, you should be able to see your update, your post, your writes or whatever. But if you end the session, finish the session, maybe it's possible that you could lose the consistency. For example, you might turn off or close your machine, close your browser, and then when you turn on or open that browser again, you may not see the post you have seen before. The post that you have made, you may not see before because the session has already ended. And then you are reading data from other different nodes that may not have the copy of the data yet. But whatever, you can see that this form of consistency, okay, is a kind of several forms that allow the system to be less strict on the consistent data, because we want to make sure that the availability, the latency, the response time of the system is fast enough. You may read the data from one node and you may update the data on the other node or something like that. But at the end, actually, with the eventual consistency concept, all the data on all the nodes will eventually become consistent. And also, with these many types of consistency, sometimes the application can be developed in the way that improve the user experience. For example, let's see that if we have read your write consistency, or if we have session consistency, right? We as a user, we feel happy because we have seen our own updates. So instead of ensuring the entire replication consistency in short time, we can relax our consistency model a little bit to ensure only read your write consistency and session consistency, for example. Alright, in summary, we can discuss that there exist several degrees of consistency, and which degree would be suitable and appropriate for your application. We need to analyze in detail. But remember, when we discuss about cap theorem, we cannot have high consistency or strong consistency at the same time with very high availability, right? We need to somehow trade off between these two. Okay, so first let's look at strong consistency. With strong consistency, okay, here, the meaning is that after the update completes, meaning that you commit your transaction, right? After the update completes, the transaction is committed, any subsequent access to that data will return the updated value. Whether you access the data from any node, any place, any where within the distributed system, you should see that updated data right away. So this is called strong consistency. The second one is weak consistency here, right? Weak consistency say that the system does not guarantee that subsequent access to the data will return to the system, will return the updated value right away. But of course, we will get the updated value after certain conditions has been met. For example, the system could guarantee that not right away, not immediately, that user will see the updated value, but after inconsistency windows has passed, we can guarantee that within 2 minutes, suppose inconsistency window is 2 minutes, then we guarantee that within 2 minutes after the update has been made, users accessing the data from wherever within the system would see the updated value. That is a weaker form of consistency. Then the next last one is called eventual consistency. So with the term eventual, right, we are saying that eventually the system will be updated. So with this case, the system guarantee that if no new update has been made, okay, no new update has been made, the system will eventually make all the updates replicated, synchronized among all the nodes. And that means all access to the data from any nodes will return the last updated value, okay, eventually. So which degrees of consistency would you allow for your system, for your application? That has to be carefully analyzed. It really depends on the requirements of your system. The cost that inconsistent data would make, the problem that inconsistent data would make, this has to be analyzed. Whether is it okay that you allow some inconsistency window? For example, if you look at social media, do you think is it okay if you post something now? Your friends and everyone in the world would need to see your post immediately. Is it that case with social media application? Or if we say that inconsistency window would be a few minutes, is it okay that we use this form of weaker consistency model and say that after a user posts something and after a few minutes pass, other users will be able to see this new and latest update value, okay? But of course, sometimes with a very serious and stricter business, Strong consistency may be the case when it is related, for example, with financial data, security. Okay, so in that case, you may need to insist on strong consistency model. Suppose you want to make sure once you have updated your money in your bank account, it has to be updated right away. You don't allow a few minutes delay or inconsistency, something like that. So, repeating what I have mentioned in the previous slide, whether inconsistency is acceptable and which degree of consistency is acceptable, it really depends on the client application and the requirements. There is again no one single correct answer for every case. It is really case by case basis. So when we have a consistency degree that is less than very strict and very strong consistency, it means that we allow certain form of relaxation, right? So consistency relaxation should be considered for two reasons, for two cases. That is, why do we need to relax the consistency? Not that we relax it for our own simplicity, right? But we consider relaxing and we consider allowing inconsistency to be tolerated because we want to improve reading and writing performance. Okay. Under certain concurrent conditions. Remember again that we are in the distributed system and we also want to allow concurrent execution, concurrent access of data from multiple nodes, multiple places, from anywhere, from anyone, and in any time, right? So we want to improve this reading and writing performance. Then we may need to tolerate the inconsistency for this reason. And second, that is for handling partition cases. That means part of the system may become unavailable. So that is what we cannot avoid inconsistency. When network partition occurs, right? If we still want to restrict the consistency, it means we need to allow only reading. We cannot allow writing because writing can create conflict of the data among the different partitions of the system, and that definitely creates inconsistency. We have discussed about asset transactions, which are important properties for relational models, right? So next we will talk about another types of transactions, which is called base transactions. The concept of base transactions could be considered as an alternative to asset transactions. So let's have a look. What does base transaction refer to? BASE for base transactions refer to first basic availability for the BA, and the S refers to soft state, and then E for eventual consistency. Okay, so these are the meaning of base transaction. Basic availability indicates that the system would guarantee availability, right? So it means that we prefer availability when considering the CAP theorem. We want the system to fulfill requests, to be responsive, but we trade off with certain partial consistency, not very strong consistency. Then the second property, soft state. Soft state means that the state of the system will change or may change over time, even there is no change made because of the eventual consistency model. Because even there is no change made by the user, but the system is still working on eventual consistency among all the replicated nodes in the system, in the distributed network system. So it also mentioned here as well that data consistency is the work that developer has to maintain and ensure, not the work to be handled by the database system. Okay, and then the last property, the last point, which talks about eventual consistency. It means that at some point in the future, right? This is the definition of eventual consistency. At some point in the future, the data will converge, will synchronize, and will be consistent. It may include some delay consistency, but it will converge and it will be eventual consistent. Okay, and this is opposite to the immediate consistency and the strong consistency model of ACID property. So base is, in conclusion, an alternative to ACID properties. This slide would discuss when should we use base transactions. So certain points that we need to consider, of course, as from the basic availability emphasized, right? With base, the base data store values the availability. So if we values availability over consistency, maybe base transaction is a solution for our application. Second, of course, we need to be aware that base does not offer guarantee consistency at right time. That means you make an update to the database system. Other users may not see your update immediately. This is what you need to be aware of. And of course, but what we can guarantee by base transactions is that data will be consistency in the future. Okay? But of course, it has to pass certain time. And in overall, finally, the base consistency model is considered to provide a less strict form of ACID transactions. So, base transactions could be a solution for your case if you consider all these criteria and you think that is appropriate for your application. So, let's summarize what we have learned. We have learned several forms of consistency model, right? That starting from very strict consistency model and also weaker forms as well as what we call eventual consistency. We also discussed about ACID transactions, the meaning of transactions, the properties of transactions by means of ACID, and also discussed about base transactions as a weaker form and an alternative to ACID transactions when we want to implement and develop our database system. So which model would be appropriate to your database application, the project you have been working on? Can you try to consider and analyze based on your own project requirements?